Rahman Rahim. Dear students, come to our next lecture. So today we will discuss about the elimination half-life. So elimination half-life T1 by 2, it is the time taken for the plasma concentration of a drug to reduce by 50% of its initial value. So as in previous lecture, we have already discussed all the parameters related to half-life. So it means that after 4 half-lives the elimination is 94% complete. So look at here, this is what elimination constant. Elimination constants, it can be represented by small k, and you can see EL. This is equal to the logarithms of 2. The logarithm of 2, so then you should take the logarithm of 2 and it will be divided by T half. As we know that T half is equal to 0.693 divided by T half. So it means this is the mathematical calculation. So likewise, look at here, this is drug clearance and this is elimination constant and this is volume of distribution. So it can be written as, so the drug clearance is equal to, then the drug clearance will be equal to 0.693 multiplied by volume of distribution divided by T1 by 2. Then it can be written as like this, T1 by 2 is equal to 0.693 multiplied by volume of distribution divided by drug clearance. So now this is the mathematical form of half-life. Of how it can be written is that half-life is equal to 0.693 multiplied by volume of distribution divided by drug clearance, and this is KL is equal to elimination constant. Now come toward pharmacokinetic principles. So pharmaco and pharmacokinetic principles, first of all we will discuss about the steady state. So what is steady state? It is the amount of drug administered which is equal to the amount of drug eliminated within one dosing interval, resulting in a plateauic constant serum drug level. So already as we have talked about the steady state, that whenever the rate of administration of drug is equal to the rate of elimination, so it is steady state concentration of drug. For example, drugs with short half-life, let us suppose drug with short half-life reach steady state rapidly, and drug with long half-life take days to weeks to reach steady state. It means that the Pareto principle is a mathematical model or scientific law originally developed to explain the time course of the drug actions and the term of pharmacokinetic. So point to be noted here, that let us suppose drugs with a short half-life, let us suppose a drug whose half-life is, let us suppose 30 minutes, or another drug whose half-life is 40 minutes, or you can say 1 hour. So the drug with short half-life reach the steady state rapidly, while the drug with long half-life will take days to weeks to reach steady state concentrations. Look at here, this is steady state concentrations, you can say statistically, and on this side look at it, this is the concentrations and doses. So it will be discussed, look at here, from 0 then to 4, 6, 8, 10, 12, 14, 16. So look at here, now this is start from this concentrations, so it will jump from 8 to 4, and then you can see here this is 12, and then onward 6, and then 14, and then onward. So it mean, and these are the, you can say, different doses. Half-life in explains in the order of kinetics. What are order of kinetics? So look at here, this is called first order kinetics. So if you remember in our previous lecture, that after completion of, after when one half, if you remembers, when look at here, look at here, I will as we have discussed plasma half-life of drug, that after one half-life the concentration must be reduced to 50%. So it means that here in this case, the same case is here. So after one half-life, the concentration of the drug will be reduced up to 50%, while after two half-lives, after second, you can say after second or two half-life, after two half-life, the concentration of the drug will be reduced up to 25%. It means that the concentration of the drug will be reduced further after 3 hours, after 3 half-lives. So the concentration of the drug will be reduced 12.5%, and after 4 interval, you can say after 4 half-lives, the concentration of drug will be reduced up to 6.25. This is called first order kinetic. First order kinetic can be defined as in simple words, first order kinetic, let's suppose absorption, distribution, biotransformation, excretion processes are mostly occurring at the rates proportional to the concentration of drug in the plasma. So this is very clear thing, that let's suppose if we are going to increase the concentration of the drug, so definitely it means that the rate of reaction will be directly proportional to the concentrations. So here in this case, the absorption, distribution, biotransformation, excretion process, they are mostly occurring at the constant rate, and this rate is directly proportional to the concentration of drug in the plasma. So what does it mean? It means that a constant fraction of drug is absorbed, distributed, biotransformed and excreted for unit times. These processes increase and the rate with increase in concentration and decrease with falling in concentrations. So in first order kinetics, the rate of reactions, this will be directly proportional to the concentrations. So it means if the concentrations, if we are going to increase the concentration, so the rate of reaction will be increases, while if we are going to decrease the concentration, so it means that the rate of reactions, it will be slower in first order kinetics. And first order kinetic, a constant fraction of drug in the body is eliminated for unit time, and the rate of elimination is proportional to the amount of drug. So look at here, this is this concentrated concentration versus times. So this is the graphical representation here. So majority of the drugs, so they are excreted, majority of the drugs, so they are eliminated in this way.